Good morning. This is me Mohit from CACD section, core CAC branch, and welcome to my tech talk on matrices and calculus. My topic on tech talk is Circulant N0 matrices. So before going on this topic on Circulant N0 matrices, I would like to talk about the basic definition of matrix, what are matrices and different types of matrices. Yes. So what are matrices? So matrices is a plural form of matrix, which is a rectangular array or a table where numbers or elements are arranged in rows and columns. They have any number of columns or rows. It might be two rows or two columns, one row, two columns, anything. Different operations can be performed on matrices such as addition, scalar multiplication, and vector multiplication as well. So introduction to matrices, we'll see the types of matrices right now. Now we see the first one is a row matrix. The second one is a column matrix. So the difference between row matrix and column matrix. In row matrix, there are only rows present, only one row present. It can be any number of elements. In column matrix, only a column of elements will be present. In a rectangular matrix, it can be of a 2 by 1, right? So it can be a row and column. So shape we can identify as a rectangle, and a square matrix is similar to square. It can be 3 by 3. So the number of rows equals to the number of columns. We say simply for a square matrix. So it can be 3 by 3, 4 by 4, 5 by 5, 2 by 2, right? So a zero matrix is all the elements present in a square matrix will be zero. It doesn't need to be square. It can be rectangle or it can be row, column, anything. So all the elements present in the matrix should be equal to zero. And a diagonal matrix is only the elements present in the trace, or we say diagonal elements only will be present. Will be non-zero integers. Remaining all will be zero. We see a scalar matrix is all the diagonal elements must be same. So it will be like 2. If you take 2 common from each row, it will be like 2i. We say 1 0 0 0 1 0 0 0 1 is an identity matrix. Right, the unique matrix, or we say an identity matrix. That is what we have just discussed earlier. Now we see upper and lower triangular matrix is we see that upper triangular matrix is like when we see the top right, all three elements are zeros, and bottom and lower triangular matrix, the bottom left will be equal to 0. Now we see introduction to N0 matrices. So definition of, let's go into the circulant matrices and let's see what are those things. A circulant matrix is a square matrix where each row vector is a cyclic permutation of the row above it. So circulant N0 matrices are a special class of circulant matrices where all the elements are non-negative integers, denoted as N0 matrices. So there'll be either cyclic permutation and there's no zero number present on that matrix. So it's important for the application in discrete systems, signal processing, and coding theory. Now these are some of the structure of matrices. We see 1, n1, like that. This is a basic general form of a circular matrix. C of order n is defined by its first row. So if the first row is C0, C1, C2, so on till Cn, n minus 1. Now, the properties of the circulant matrix is each row is a cyclic permutation of the previous one, as we discussed earlier, and the matrix is diagonalizable using the discrete Fourier transform (DFT). This is a method to find the eigenvalues as well. We'll all deal with that later. So, non-negative circulant matrices N0. This is a common example, as you see, it's a 4 by 4 matrix. So, circulant N0 matrix is a circulant matrix where all elements are non-negative integers. Consider a circulant matrix N of order 4. So order of n4. So it's a 4 by 4 matrix we see. So the n matrix is an n0 matrix because all the entities are non-negative integers. So the properties with this circulant matrices are symmetric under the cyclic permutations, and their eigenvalues are computed using the discrete Fourier transform in the first. So I'll tell you how the formula, its procedure, and we will solve the problem as well. So they have an algebraic property like closure under addition and multiplication, the determinant and trace dependent on the entries of the first row. So applications of circulant N0 matrices, signal processing. So used in modeling of filters and systems with periodic or cyclic behavior. So fast algorithms for convolution due to circulant structures. So cyclic permutation is easy for a circulant structure. So let's take an example. When performing circular conversion of discrete signals, the operation can be represented as matrix vector multiplication using a circulant matrix. So due to their structure, circulant matrices can be diagonalized using the discrete Fourier transform method, DFT method, allowing for efficient computation of conversions and other operations as well. Now, error coding codes in coding theory. So cyclic codes. So circulant matrices are foundation in the constructor cyclic codes, a type of linear error correcting code where the cyclic shift of any code word is also a code word. So let's take an example. Generic generated matrices of cyclic codes are often circulant, which simplifies encoding and decoding as well. So efficient implementation is also possible. The structured nature of circulant N0 matrices reduces complexity of encoding and decoding algorithms in communication systems. So let's see the graph theory. So yeah, Python is being used right now in graph theory. Let's see on maths perspective on the point of view. So adjacency matrices of cyclic graphs. So in graph theory, circular matrices are used to represent the adjacency matrices of circular graphs, which are graphs where the adjacency relationship is invariant under rotation of vertices. So applications include study of networks with regular cyclic connections, modeling and analysis. These materials or matrices we see help in analyzing network properties like connectivity, eigenvalue spectra, and symmetry. So computing eigenvalues. Now we have know what is a circular matrix, what is an N0 matrix, which is related to the circular matrix. Now we'll see how to compute the eigenvalues for a given circulant N0 matrix. So eigenvalues of circulant matrices. So eigenvalues of a circular matrix C with first row we know already covered C0, C1, so on to Cn-1 can be computed using the discrete Fourier transform method. So we say that lambda k is equals to j is equals 0 sigma from j 0 to n minus 1. This is the summation limit cj dot omega n jk for k0, k1, k2, so on to k n minus 1. So where omega n is equals to e to the power of 2 pi by n is the primitive nth root of unity. We know the square roots of unity. So omega plus omega square plus omega cube equals to 0. So for N0 matrices, eigenvalues are real and non-negative integers. So this is a common example we see right now. The question given for us was consider the circulant N0 matrix. So we have an N0 matrix here. Find the eigenvalues for this matrix. So we see the solution. Step 1 is to formula for the eigenvalues. We have given eigenvalues nk for a circular matrix C with the first row C0, C1, C2, so on till Cn. Now lambda k is summation of from J0 to x minus 1, x minus 1, Cj dot omega n jk. So where n is the order of the matrix or size of the matrix, we say order basically. So here n was 3. It's a 3 by 3 matrix we can see from the question. And now where omega is e to the power of 2 pi I pi n is the primitive nth root of unity. And k ranges from 0 to n minus 1. So our first row, we see in the question our first row is 2, 1, 0. So for n equals to 3, the roots of unity. So calculate omega for each thing. Okay, so like omega 3, 0, omega 3, 1, and omega 2, 3. So we get omega 3, 0 is 1, 2 pi by 3, and 4 pi I by 3. So these are for omega 1, 3 is minus 1 by 2 plus I root 3 by 2. Omega 2, 3 is minus 1 by 2 minus I root 3 by 2. And for step 2 is to find the eigenvalue computation. So for k equals to 0, 1, and 2. Okay, these three things, right? 2, 1, 0, 0, 1, 2. Compute lambda k. So we have k equals to 0. So lambda 0 is equals to z0 plus c1 omega 0, 3 plus c2 omega 0, 3. So it's 2 into 1 into 1 plus 0 into 1. So it's like 2 plus 1, 3. And we have for k equals to 1. Similarly, we find out. And for lambda, yeah, c0 plus c1 omega 1, 3 plus c2 omega 2, 3. So we get 2 into 1, 2 into 1 plus 1 into minus 1 by 2 plus I root 3 by 2 plus 0 into minus 1 by 2. So the whole term is 0. So this whole term is 0. And we get lambda 1 is equals to 2 minus 1 by 2 plus I root 3 by 2. So it's x3 by 2 minus plus I root 3 by 2. Similarly, we can find for k equals to 2. We see that lambda k equals to c0 plus c1 omega 3 2 plus c2 omega 3 1. So we can find like that. We get 2 minus 1 by 2 minus I root 3 by 2. We get just minus 3 by 2 minus I root 3 by 2. Now, to verify these are the eigenvalues for that resultant N0 matrix, what we can do, we can just add the traces, right? So you can get 2 plus 2 plus 2, right, is 6. From the given question, 2 plus 2 plus 2 is 6, right? So now let's add the lambda 0, lambda 1, and lambda 2. So the respective eigenvalues, the summation of these eigenvalues should be also equal to the trace of the N0 matrix. So it's 3 plus 1, 3 by 2 plus I root 3 by 2 plus 3 by 2 minus I root 3 by 2. So I root 3 by 2 and I root 3 by 2 cancels as their opposite signs, and 3 by 2 plus 3 by 2 is 3. So 3 plus 3 is 6. So in conclusion, we see that summary, circulant N0 matrices are a special type of circulant matrix with non-native integer entities. So they have an important applications in signal processing, coding theory, and graph theory as well. So the structures allow efficient computation of eigenvalues and matrix operations. For future work, we can also view further researches on the use of cryptography, and machine learning as well. Thank you.